What I'm hearing here is search for the source of the common mode voltage and insulate or reduce the amount of voltage getting to your affected conductors rather than trying, let's say, common mode filters, common mode chokes, unless you really need them or you can prove that you need them.
Oh, that's right. We never design in a common mode chokes for balanced power inputs or unbalanced signal ports make perfect sense. We see common mode chokes on unbalanced power inputs, which actually makes no sense. But common mode chokes is a different thing. Ferrites, on the other hand, just clamping a ferrite around a cable, a great tool if you're troubleshooting and just need something that's going to give you a few dB quick. We would never design that in.
Hello, everyone, and welcome to the Altium OnTrack podcast. I'm your host, Zach Peterson. Today, I'm very happy to be talking with Todd Hubing, president of LearnEMC. Now, I first came across Todd and LearnEMC long ago when I was searching the web trying to, learn EMC. And so I'm very happy to be talking with him today about all sorts of things with EMC and PCB design. Todd, thank you so much for being here. I feel like we should have done this a lot sooner because I have seen you online many times. So I'm very happy that you agreed to do this.
I'm happy to be here.
Absolutely. So, if you could just briefly, because I know you're more experienced than I am, give us just a quick overview of your background so that people know who you are.
Yeah, the short story is I started in EMC working with IBM, 1982, so quite a while ago. I worked for IBM for 7.5 years. And one of the things I enjoyed doing at IBM was teaching. I taught a class at North Carolina State in EMC, and I enjoyed doing research, but those were not my main job. My main job was product support. And so after 7.5 years at IBM, I had an opportunity to go to the University of Missouri-Rolla, which is now the Missouri University of Science and Technology, and be a faculty member where I could do teaching and research all the time. And I did that, and I was there for 17 years, and my colleagues and I there really spent our careers doing EMC research, trying to figure out why is this the way it is, how are these signals becoming this radiated noise, trying to develop algorithms to formalize it or do as much on a computer with a computer as we could. We also were developing numerical electromagnetic modeling tools. And then I had an opportunity in 2006 to go to Clemson University with an endowed chair position in vehicle electronics. And so I did. I went there and built an EMC laboratory there and continued to do EMC research. And then I retired in 2015 and moved to Stoughton, Wisconsin, and I've been doing consulting and teaching courses since then.
Yeah, that's a long, illustrious career. And it sounds like you kind of came into the industry at a time where people were, I guess, learning that they need to care quite a bit more about EMC, because I think this is right around the time where a lot of digital signals were starting to get fast enough to cause those EMC problems, which is kind of the story from the signal integrity side.
Yes, I also joined the year that the FCC requirements kicked in fully and became mandatory. That's not coincidence that IBM was looking for people in EMC at that time. Yeah, so all of a sudden, companies that didn't have regulatory requirements related to electromagnetic compatibility did, at least for radiated emissions. And that caused a furious activity in the field at that time.
So it's always nice to get the historical context a little bit, but behind EMC, and I think the why of the regulations is always nice to know, right? I mean, we kind of, today looking back, we of course know, yeah, devices can interfere with each other if not designed properly, but back at the time, what exactly was going on in the industry that drove the creation of the standards and regulations?
I think largely just the widespread use of microcontrollers, microprocessors in products that people were bringing into the homes. IBM had been doing electromagnetic compatibility testing, and they had their own requirements for years prior to that, but IBM didn't sell stuff into the home. And I think when things started coming into the home, all of a sudden we were seeing a lot of interference, or the FCC was seeing a lot of interference complaints, and decided they needed to do some, at least regulation of conducted and radiated emissions.
So it sounds like before the FCC got involved, companies kind of did their own thing. They had their own standards that they would enforce for their own products. And that, of course, lends itself to the case where, well, product A and B might obey what we call some kind of, EMC, but products B and C may not.
Yeah, that's right. And it also, from country to country in Europe, every country in Europe had their own requirements. And Germany, which had the strictest requirements at the time, at least that I'm aware of, they also regulated immunity, which the US did not do. And so a lot more activity took place in the mid 90s when the European Union formed, and all of a sudden, to legally ship to most countries, or to the European Union, you had to meet immunity requirements as well as emissions requirements.
I see. I see. Okay. Yeah, it's great to have that context and really see, how all of this developed. And I think this is something that new designers really don't think about until either they kind of stumble across it online, or until they start working their first job, and then some people start talking about EMC, and it's like, well, what is this? Why do I have to think about this?
Yeah, when I was in Missouri, it was a public university, and so we would do free consulting for Missouri small companies, basically. And we had lots of people come in. They got a great idea. They built a board. They went to sell it, and they had to get an attorney. And when they got an attorney, the attorney said, "Oh, you're going to have to take this to a test lab and get it tested for electromagnetic compatibility," is something they had never thought about or heard of. And all of a sudden, usually they did not pass, as you might imagine, even back then. It's not that the requirements were difficult to meet, but if you weren't even aware of them and you weren't designing to them, you usually didn't by chance meet them.
So over time, a lot of PCB design guidelines, and I think more broadly, some system design practices, you might say, have sprung up out of all of this. And I'm really interested to know, like, how do we arrive at some of these best practices, and how do some of the myths and facts start to develop over time? Because you've been kind of vocal on this, and I know you do some you do webinars where you talk about some of this stuff. So I think before we get into those points, maybe if you could just kind of tell us how some of those best practices got developed, and how they turned into myths.
Yeah, and of course there are a lot of them, and they all have their own history. One of the big ones, I think, was grounding, and all the problems people have with grounding. Back in the 80s, I think we understood grounding pretty well. But what happened was, what people didn't understand back in the 80s, what digital circuit designers in particular didn't understand, was that these signals had a current, and it wasn't good enough to just get the current out to the device, the load device. That current had to come back. People, they tend to think of the signals as voltages, and you just got the voltage there. It was relative to ground, and you didn't think about current and current having to come back. And that worked okay when things were very slow at kilobits per second. But in the 80s, we were starting to get up into the megabits per second, and people were having problems because they didn't pay any attention to how the current came back. And when Henry Ott wrote his book that he published in I believe it was 89, he had a sentence in there, digital ground is a path for returning currents to their source. I believe I got that word for word what he said, because the idea we were trying to get across is you've got to pay attention to the current. It's got to come back. And this thing called ground is what it's coming back on. And we were really pushing that in the 80s and the 90s. Ground is a path for returning currents to their source. And what happened was, I think that idea has gotten out there pretty well now, but we lost what ground was, because ground is a legitimate EMC function that we really rely on in design, and that ground is not a path for returning currents to their source. In fact, if you return high frequency currents on that ground, it's not going to be a good 0-volt reference anymore. You're not going to. So a lot of our rules for grounding are kind of a mixture of what was grounding, and then safety ground also in there. So we have 3 different kinds of ground, all with their own rules, and those rules just kind of got confused. And then it didn't help that most of the boards being built back in the 80s had 1 or 2 layers, mostly 2 layers. And then maybe you had 4. But if you got 4, it was because you had so many signals to route that it was hard to get a solid plane in there. And so this idea of dividing grounds, so you don't divide grounds. The safety ground, you don't want 2 safety grounds. EMC ground, you can't have 2 EMC grounds. But current returns, sometimes you have to divide current returns in order to avoid common impedance coupling at low frequencies. And so there are legitimate reasons to keep things labeled ground isolated. But rules were formed, and particularly as frequencies, at high frequencies, that's not the case anymore. At above a megahertz, the currents come back. You provide a good path for those currents, and they take that path. So it doesn't matter that they're on the same plane. They're in different places. But at low frequencies, there are sometimes legitimate reasons to have isolated grounds. But if you ask ChatGPT how to do my grounding on a circuit board, they're going to go back to this. It'll generally tell you need to have a solid plane on your circuit board, but then it'll tell you to use a star ground or do just crazy stuff. Anyway, there's a lot of confusion surrounding grounding, and it doesn't help that a lot of people that come from a signal integrity background, and in signal integrity, ground is a path for returning currents to their source. That's their main. You don't have a good 0-volt reference at one end of a high-speed line, compared to the other end. They each have their own local 0-volt reference. And that's an idea that's also true for EMC ground. But for signal integrity people, they don't need to consider EMC ground or safety ground. The ground is a path for returning currents to their source. But if you're the EMC person and you need to meet a radiated emissions requirement or any of the immunity requirements, you should have a pretty good idea of where your EMC ground is, your ground structure. Where are those currents being routed to on your board or in your module or even in your system?
So you're mentioning EMC ground, and I think that's a term most people would not hear. Normally when people talk about ground, they have their system ground, which could be your digital ground, right? They could have a chassis ground, right? Maybe you have a metallized enclosure, and then they could have an AC input with an earth connection. So then there's also an earth ground. So there's at least 3 grounds, right? And then maybe if you have an isolated DC-DC converter, there's another ground somewhere else, which is isolated from some other ground. So you can kind of see how you start to get all these different grounds, but you're using the term EMC ground. So what do you mean by that in relation to those points that I mentioned?
Yeah, so EMC is your local 0-volt reference. So it's different at the board level, module level. So at a module level, if your module is mounted in something with a chassis, that chassis ground is your EMC ground structure. Ultimately, if you had noise currents coming in on a cable from some external source, your job as a module is to get those currents to the chassis. After that, you don't have to think about them anymore. That was a system level thing after that. But or if you're on the circuit board and the circuit board has any kind of a metal mounting on it at all, your job is to get those currents to that metal mounting structure. And once you get them there, they're not going to come back onto the board. And so it's where we're trying to send those currents. Or from an emissions standpoint, it's half of a really good antenna, and it's there. It's something in your board or system that's big and metal, and it's there. And as long as you don't drive anything else at high frequencies with more than a millivolt, you're going to meet radiated emissions. And so once you've identified where's the big thing that's half of the antenna, then we want to try to bond everything. Well, we have two options. We can either bond things to that ground in order to keep it from becoming the other half of the antenna, or if we've got some other metal, as long as we don't drive it. So it's okay to have big metal somewhere else as long as your circuits can't drive it. And then maybe your circuits can't drive it because it's too far away. Because if we have to electric field couple to it, by the time we get some distance away, our fields are not going to drive it anymore relative to our ground structure. Or the other thing that we can do is slow down our sources or make bandwidth, limit them to ensure that we're not developing enough voltage to drive anything. So go ahead and let it come close to our circuitry. There's not enough voltage there to be a problem.
I think this is also where someone might bring in like something like shielding, right? To try and prevent driving that big piece of metal.
Mm-hmm. That's right. But once you visualized it, once you say, well, here's the big piece of metal that I'm going to call ground, my EMC ground, that's half of the antenna. I don't need to shield that. I don't need to keep currents from going on to that, because that's my 0 volt reference, my local 0 volt reference. As long as everything else that's big and metal gets tied to that 0 volt reference, and I don't return any high frequency current in that reference, because if you return a current in a piece of metal, it creates a magnetic flux that produces a voltage. But as long as I don't return current in it intentionally, I can just tie things to that structure, and that prevents me from driving them hard enough to be an emissions problem.
So if you had, maybe tell me if this is the explanation you would use, right? If you had a digital ground, right? Let's say your system ground in your PCB. Let's say you're just using a ground plane, right? And this is the path for return current, as Henry Ott calls it, right? You can also have a larger piece of metal, let's call it your chassis ground, right, somewhere. And really the goal behind connecting those two is to just eliminate the potential offset between them, but not to necessarily pass the return current into this chassis ground. Is that an okay way to say it?
Yes, yes, it is. And certainly the high frequencies where we're worried about radiated emissions, the current won't just go wandering off. People get very concerned about current just going off, finding a path that's going to cause the high frequency currents. If you give them a good path, they tend to take that path. They're not going to just go wandering off, causing problems for you. Where we run into problems is when people don't give the return current a good path. And there are a few other ways you can run into problems, but basically what you said is a good way of succinctly saying it. If everything that's big and metal gets bonded, it's hard to drive it hard enough to cause an emissions problem.
Sure. So this is where you get these guidelines that I think kind of look like a star ground, where maybe you connect your chassis back to your PCB somewhere at a point where it's mounted, and that's good enough, right? Because like you said, if you already give a good let's say low reactance return path to a digital signal, it's going to continue to follow that. It's not going to stray through your screws onto your chassis and then just run that way.
That's right. So you really could connect it to the chassis at both ends. The current will still come back on that copper plane. But all the cables coming in need to be filtered back to that EMC ground, or the chassis ground structure. And if you don't have the chassis and you just have the circuit board, we still use the side of the plane under the I/O connections over there. That's our 0 volt reference. Everything that leaves the board gets bonded to that part of the plane. And then you can't run any signals parallel to that edge, or you'll create a voltage across the edge. But So then, yeah, so we can have an EMC ground on a circuit board that doesn't have any chassis at all. We just need to make all our connections on the same edge. Yeah. And if people say, well, I can't make all the connections on the same edge, I have to have some on this edge and some on this edge. That's okay. But then you need to have that chassis because the potential at one side and the potential at the other side, if you've got high-speed circuitry in between, are not the same. And so you can't have some cables reference to one potential and some reference to a different potential.
Sure. And then I think the last question I have on grounding is, I often hear someone bring up, like, if you have let's say multiple mounting holes that then connect to your large chassis ground, they'll say, oh, well, I can trace out a loop there, therefore I get ground loops, and my digital signals are going to cause ground loops. Well, how would you respond to that?
Yeah, so the high-speed part of it, the stuff that's a megahertz and faster, will not go down onto the chassis, and that ground loop being there won't impact that at all. If that ground loop were a problem for some reason, it would have to be a low frequency coupling, which you could have a chassis that's got 100 amps of current flowing through it because of some other machinery connected elsewhere. And maybe you don't want a fraction of that 100 amps of current coming up onto your circuit board because there's some other, again, low frequency receiver that's sensitive. So there are ground loops. Ground loops, if it's really ground, are not a problem ever. But if the thing that's forming the loop includes a current return, well, then that could be a problem. You've given low frequency current multiple paths, and you have the potential for common impedance coupling. But my advice is we never isolate anything called ground unless we've done a calculation to show that they need to be isolated. Because usually when you do that calculation, you say, no, I don't care. The worst case common impedance coupling at low frequencies is not going to be bad enough to be a problem. So it's very rare. When I see digital ground and analog ground on a circuit board, there are some rare situations where that makes sense. But if you do the calculation, you realize, no, most of the time, there's no reason to isolate those.
Sure. Yeah, I think that last point about the analog and digital ground is, I talked to Dan Beaker about this at PCB West, I think a couple of years ago, and he had mentioned that this is probably an unfortunate problem due to pin naming in data sheets, where the pin naming almost implies that you should have separate ground because they name the pins A, G, and D and D, G, and D, right? So, of course, if you don't just read the next few pages in the data sheet where it says to connect them with a plane, you would think, oh, they have to be different grounds.
Right. Yeah, that's definitely a problem.
Yeah. Well, I guess until the data sheets change, people will continue to do it wrong. If we could, I'd like to shift gears here to something else, which I saw on LinkedIn. Someone named Rolf Ostergaard, who does some signal integrity courses and seminars and things like this. He actually brought up something interesting that you had said, which is about decoupling, and I believe he was citing an older IEEE paper, which you were an author on. About placement of decoupling capacitors. So if you could tell us about some of the proper circuit board decoupling strategies. And I see your smile here because there's going to be, I think, a lot of confrontation to the standard design practices.
Yeah, and it's hard at a podcast because there's a one-day course I teach just on circuit board decoupling. So there's a lot to it, but the particular LinkedIn article you're mentioning, that was written 30 years ago. And it was a project we did that was funded by Boeing. And what we found was we were kind of surprised to find that the location of the coupling capacitors didn't make any difference. And when we finally got down to modeling it and modeling it correctly anyway, we realized, no, it doesn't make any difference. Again, somebody then pointed out, wait, we're talking about closely spaced power and ground planes, 10 mils or less apart. So they have the very low inductance associated with waves moving between those planes. very low impedance associated with moving through those planes. There's a lot of inherent capacitance, so at the highest frequencies, you actually get a lot of current from just the plane capacitance. So there's a lot of caveats in there. But if you have closely spaced planes, it's not going to matter where the decoupling capacitors are. At low frequencies, the location is not going to be important. And when you get to high enough frequencies, you're going to find that they're all connected through too much connection inductance to be very effective compared to the planes, which become a very good source at that point. So yeah, the location doesn't matter. And there were a lot of comments on there. And it was interesting because Robert Fernick had done a video, and he had modeled decoupling on circuit boards with decoupling capacitors in various positions, and he showed, the location was very important, and it was very important. And somebody pointed out, you've got 40 mils of spacing. He had at least 40 mils of spacing between his two planes, so they were widely spaced planes. And if you have widely spaced planes, it's a completely different model. We can make that work very, very well in terms of decoupling, but what's going to happen is the closest decoupling capacitor is going to be the one doing all the work. Not all the work, but most of the work. So location is very important. So then Robert did another video. He changed his stack up to where he had the closest spaced planes, and then he saw, oh yeah, you know what? I put the decoupling capacitor right between my his input and output for his S parameter measurements. And here he put it way off to the side, and you got the same result, essentially within an ohm of being the same power bus impedance. So yeah, it's not intuitive that location doesn't matter. But we see that with ball grid arrays. You've got a board that's got 4850 layers. You've got a BGA. It's got a dozen 3.3 volt input pins. So you wouldn't have a dozen input pins unless you were going to draw a whole lot of current very fast. So that needs very low impedance power bus. And in the design recommendation, you want to get that plane pair as close as you can to that BGA. So you've got 4050 layers, and you're on layer 4 and 5 are your power and ground pair, perhaps. And then the design recommendation says, we'll put decoupling capacitors on the back side of the board, directly connected to the vias that go to the balls. And I don't have any problem with that, because you can't use that space for anything else. That's a good place to put decoupling. But every decoupling capacitor located on the top layer is going to work better than those that work directly connected to the balls, because the planes were up close to the device. The device needs current. It draws it from the planes very quickly and very efficiently. And that basically, as it's drawing, it depletes all of the voltage in the planes for any reasonable size board. All the decoupling capacitors on the top have started to respond before the ones on the bottom can start effect, because they're connected through too much connection inductance going all the way through the planes. But it's a lot about inductance. It's not all about time of flight. In fact, it's that kind of bothers me when I hear that, because yes, that depletion wave between the planes went past that first decoupling capacitor at some time. Let's say, it took, to get to the first one, it took 100 picoseconds, and then to get to the one over here, it took hundreds of picoseconds, but it didn't matter. It saw that first one, but that first one was connected through too much connection inductance. It's too slow to respond. Or, as Ralph Morrison might point out, if you don't want to talk about connection inductance, you have to talk about the impedance associated with that connection. So yeah, it's a little short transmission line going up to the capacitor, but that's like 100 ohms of characteristic impedance, and you were in something that was a sub-ohm. So you can't draw, it's a short transmission line, but you can't get much current out of it. You've got to send a wave up to the capacitor. Capacitor looks like a short. You get a wave, so you're going to bounce back up and down on that little short transmission line many, 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 many times before you start to get significant current out. And by then,
Interesting.
you've got to all the other capacitors on the board. And it's not just a mind experiment. Basically, every simulation that's done correctly anyway, you see that this is true. All of the capacitors are basically contributing equally on normal size boards. For me, normal size is something like that. If very big boards, of course, the stuff that's way off is not close enough to be helpful as soon as it could be helpful. But on normal size boards, the location is relatively unimportant.
Yeah, this is interesting, right? Because two things here, right? You're saying, you put the ground and power plane pairs together on a normal size board, and the capacitors just need to be close enough. They don't need to be like right up next to every single pin. But you have identified a couple of good reasons why you might do that. I think that the use of space on the backside of the BGA makes sense, especially as you start to go up in density. The other factor here that's always interesting about PCB design guidelines is it's that asterisk that comes with the guideline, right? The decoupling capacitor position matters way more when you don't have the power ground plane capacitance. And I think that's what gets lost in this discussion about decoupling capacitors.
That's right. Yeah, and it's not just the lack of capacitance. It's you get a mutual inductance between the vias from the decoupling capacitor and the active device when you've got widely spaced planes, which is greater than the connection inductance outside the planes. And so you actually kind of, like a transformer, you pull current out of that nearby decoupling capacitor. On say 4-layer boards or 6-layer boards where the power and ground are not on adjacent layers, if you share the via connected to the most distant plane, which is usually the power plane, if the capacitor and the active device share that via connection, you've maximized that mutual inductance. That works really well. That one capacitor is supplying more charge than the planes are. And they're doing the work of the decoupling. And it works great. In terms of keeping noise off the planes, which EMC people like to see, that works really, really well. In terms of getting charge quickly to the device, that doesn't work as well as closely spaced planes. And I usually
well, and then there's the frequency band as well that you can supply, because the capacitors themselves, they have some inductance, effective series inductance, and then you're mentioning that there is some inductance in the connection, and that limits the effectiveness up to some high frequency. But then at some point the planes take over, which is kind of what you're suggesting here. And the fact that the planes can take over and continue to extend the bandwidth where power can be supplied to those pins. That's the other reason that we use the planes.
Yes.
Okay. So this is, of course, really interesting. And I think it relates to another really important point that you talk about, which is how to make board layer stack up decisions, right? Because, of course, the decoupling strategy is not just where you place the decoupling capacitors, but you just mentioned a power and ground plane pair. So now we have to place that somewhere in the stack up as well. And I will be honest, something I haven't always thought about, or I've thought about it, but not really discussed it so much in some of the multi-layer boards that I've done, is where in the stack up are the power and ground plane pair, right? You mentioned, let's say you have a really high layer count board, and you put the power and ground plane pair closer to the BGA, let's say that needs that power, it's much more effective than putting it lower in the stack up. And I guess it's because of the via distance.
Yeah, that's right. And in a lot of boards, you only have those high pin count BGAs on one side, and everything on the other side is relatively slow. So we want that plane pair toward the top. If you've got, and we've seen this a lot, you've got BGAs on both sides of the boards that are drawing tons of current, then you probably want two plane pairs, one near the top. If you've got 50 layers, you want two plane pairs, one near the top, one near the bottom, to get the current to both devices as fast as possible. But yeah, the stack up problems in general, I don't like it when people say this is a terrible stack up. Because maybe it was a terrible stack up for certain applications. But when I started working in automotive, I was basically exposed to a new world where they have everything from the autonomous vehicles with 48, 50 layer boards. They've got, and everything, lots of very high speed communications. They've got that. But you've also got a lot of sensor boards and stuff sitting out there, 4 or 6 layer boards that there's a microcontroller on it and a sensor, and nothing high speed at all, because they're sensing something mechanical or thermal. That's always slow. The communication is usually CAN, which is high speed CAN is like 5 megabits per second, and it's differential. That's not particularly noisy if you do that well. And so everything's slow. So your stack up, actually, in a lot of cases, why do they have a 6-layer board? Well, they have a 6-layer board because they thought they needed to have 2 ground planes, because with a 4-layer stack up, people say, oh, you need to have ground on layer 2 and ground on layer 3. Well, maybe sometimes that's right. But no, not you. If we're using a 4-layer board, it's probably because we didn't have a whole lot of high-speed I/O. And if you've got a limited number of high-speed stuff, you could do that with just the ground on layer 2. Anyway, the optimum stack up's really going to depend on your application. And I kind of don't like to hear when people say this is a terrible stack up without defining what the application was.
Right. No, and I would agree with that. I think the one stack up that I think gets misused a lot, frankly, but also gets called terrible all the time, and I've done it myself without providing the context, is signal ground power signal for a 4-layer stack up. And I've done boards on signal ground power signal, and you did it because the power plane was there for high current, right? You had it's a power system. You're probably filling the back layer with ground anyways. You need a lot of current. Throw a plane in there, right? Makes sense to me. And you don't have a ton of stuff on the top side, and now you've got this leftover layer because, again, you don't have a lot of components. What do you think of that stack up?
Yeah, no,
love it or hate it.
I've seen it on a lot of boards, and I thought it was fine for what they were doing. It was fine. Power planes get used more often than they're actually required. So if you got a 4-layer board, did you really need a power plane? There are in some cases, the answer to that is yes, but in most cases, I would say the answer was no. So why did you even route power on a plane? Why not have 2 ground planes and route power on another layer? If the answer to that is you can't route it on 4 layers if you do that, then no. Don't add more layers just because you're trying to follow some stack up rule that you read somewhere on the internet. Just need to put some thought into your stack up and make sure it makes sense.
I think one of the reasons people will throw the power plane in there and make it a solid plane everywhere is because it's convenient, right? They have a lot of stuff everywhere that needs 3.3 volts or whatever. And so it's just like, well, just put a plane in there.
Mm-hmm. And I think that's fine, because if you can afford to devote the whole layer to power, and remember, we can do decoupling with widely spaced planes just as well as for EMC reasons anyway, just as well as we can with the closely spaced planes. So having power on a more distant layer is fine from a power bus noise standpoint. People will point out if you're using that power plane as a return path for a high speed signal and you come up through, you've got to take care of that return current, but you shouldn't be doing that. Now you probably shouldn't be having a power plane. If you've got so many high speed signals you can't put them all on the top layer, then maybe you shouldn't be devoting a whole layer to power.
Yeah, and that's what I've always said to people, and I think this is where someone will say, well, a 4-layer board is really expensive, so now a 6-layer board is even more expensive. So, but I want the power plane for the convenience, but I have to put signals on both layers. So then they put the signals on the bottom side below the power plane. And how do you provide ground there for those signals, right? I think that's where they then start to see, okay, now we have to pour copper everywhere on the surface layers in order to get a ground reference.
Yeah, something I really don't like to see.
I would agree, right? I think people kind of force themselves into it because there were other decisions they made which were suboptimal, and now it kind of becomes a Band-Aid. Would you agree with that?
It's a Band-Aid, but also we see the copper fill on layer 1 when there's a solid ground plane on layer 2. And that, I used to say, I don't care. We did something back when I was at UMR, so at least 20 years ago. We were trying to show the advantage of a copper fill when you have we couldn't even contrive a situation where that copper fill helped at all. In terms of crosstalk, it really, you'd think, oh, I'm catching those field lines. You're not. If you only had to go 10 mils down to find the actual ground, the copper fill guard traces, they don't do enough to warrant the trouble that they can cause. I used to say I didn't care if people filled the layer 1 with copper. It doesn't hurt. It just doesn't help. But then the problem was people couldn't avoid connecting to the copper fill rather than the plane. The current needs to get back to that plane to get back where it came from. And if it has to go looking around on the copper fill to find a via down, or particularly if multiple devices are finding the same via down, you've created problems. And so now I had an experience with one company where I pointed out, you're failing because of this. You're basically, you've got these devices sharing the same copper fill in it. I said, get rid of the copper fill. And they said, well, can't we just put vias where the ground is? I said, okay. And they went off and relayed out the board and came back. And sure enough, they had fixed the problem where I had pointed it out, but there were other places where they were still. And so now my position is I don't want to see copper fill because it appears that people can't avoid connecting to it or the robots or whatever who is laying out this board are just going to connect to it, and we don't want that.
Right. I think one reason the copper fill arises is because there was one spot where they actually did need it for whatever reason, right? Pick your reason, but then they have to put it everywhere else to balance the copper, right? To help deal with warpage.
Right. And those are valid. Copper balance or heat, pulling heat away from something. Those are valid reasons to have copper on the outer layer. And so I wouldn't, if that's the reason it's there, I'm all for it. But if it's there because you think there's some EMC advantage, it shouldn't be there.
Sure. And then the other thing you mentioned, which is really interesting, is crosstalk. And I always point out to people that Eric Bogatin has noted that in order to fit an appreciable amount of copper in between two traces to try and prevent crosstalk, let's say, you already have to space them out far enough to where the crosstalk is low enough.
Yeah.
Yeah. So I guess people aren't really noticing that part of it. And then, you start to look at how guard traces work and kind of, you can start to see, oh, copper poor is basically like having these big shorted guard traces.
Right. And there are plenty of papers out there that show that the copper fill. Now, if you have to go a millimeter down to find that ground plane, then that copper fill is helping for very closely spaced. But if you only have to go a quarter of a millimeter down to find that copper plane, there's virtually no situation where that copper fill is going to be warranted for reducing crosstalk. Just space those traces.
Yeah, makes sense. So I think the last thing that we want to bring up here, because we are getting up here on time, is something else that I think new designers might have trouble with conceptually, and then which is one of those problems that anyone dealing with EMC has to face at some point, which is common mode currents. So if you could tell us about common mode currents and how they arise and how you deal with them.
Yeah. So if you've got currents going out on a transmission line, going out on a, say, trace, coming back on the plane underneath, going out on a wire, coming back on another wire next to it, that's differential mode. All of our transmission line modeling, that's all differential mode. And differential mode virtually is never going to cause a radiated emissions problem unless you've done something horribly wrong. But in any reasonable design, it's not a problem. We can send a gigabit per second, 10 gigabits per second through twisted wire pairs throughout a building and not have a radiated emissions problems because we keep everything differential. And also power is often distributed differentially. And so noise on a power bus, as long as it's differential, doesn't cause radiated emissions. So if you've got all of our intentional power and signals are differential, but if we have a radiated emissions problem or a high frequency conducted emissions problem, that's almost certainly a common mode. So how does something that's differential mode become leaked to the common mode or converted to a common mode? And there's only one way. You've got to have a change in the imbalance factor associated with that transmission line. That is the absolute only way. You only get common mode to differential mode conversion if you see a change in the imbalance. And it's not imbalance. A microstrip trace is very unbalanced. You've got a thin trace, you've got a wide plane returning. For a common mode current flowing on that, there's a lot more current on the wide trace than there on the wide plane than there would be on the trace. But if you're flowing through a microstrip trace and then suddenly you go into a differential, a twisted wire pair, a balanced transmission line, you are going to create a big common mode source at that point. And I've seen a lot of people basically suggesting, because they're following the current. They say, oh yeah, the current went out on the trace, it came back on the plane, it was close by. Then I got into these wires, the current went out on the trace, it came back on this wire close by. So I'm all good. But they lost the bigger picture, because when they made that conversion from the unbalanced microstrip trace to the balanced twisted pair, that change in the balance created a common mode source that drives the twisted pair relative to the board, the microstrip trace, which is largely the board. And that's one way we get common mode currents. I've got a presentation talking about radiated emissions where there's basically four ways that we create it. Three of them are related to unintentional changing the balance. The other way is we can just drive a common mode current directly. So you might have a switching power supply and the switch node is connected to a heatsink. Well, you're just driving the heatsink relative to everything else, like an antenna. You're creating a common mode current. It wasn't a change in imbalance. You were just directly driving a common mode current. So there are a few ways we can get these common mode currents, but it's really a very few. It's not as if currents go wandering off and finding paths of their own and become a common mode current unintentionally. That doesn't happen.
Yeah, the finding a path to create a common mode current kind of aligns with what you said earlier about the currents or the return currents generally confining themselves to whatever that path of least impedance or least reactance is. But one thing that is sometimes cited as creating common mode currents is coupling, and I think you mentioned it with the heat sink. Not just coupling to, let's say, a large piece of metal like a heat sink, but to just pick two conductors, right? And they both have some parasitic capacitance to a source, and then that creates the common mode current. Is that correct?
That's right. If you're coupling unequally from the two sides of your signal. So yeah, that certainly happens.
So I think when this comes up and people look at, okay, what can we do to reduce common mode currents, right? Let's say you've identified two conductors, right? And you know through measurements, okay, there is a common mode current on these two conductors when this device is in operation. How do you do something about it? Do you just find the nearest common mode choke on your part distributor website? What do you do?
Yeah. Common mode chokes is almost a whole nother podcast topic, because I see those inappropriately used all the time. But if you find common mode current, if you have radiated emissions problem, it's because you had a common mode current. And if it was below a few hundred megahertz, it's like you had a common mode current on a cable, something long, and you were driving one cable relative to another, or a cable relative to your chassis. So yep, you have that, and the amount of radiated emissions directly proportional to that current. Do you control that current in an EMC test? No, you don't, because in an EMC test, who knows how they're going to arrange the cables. Moving a cable a little bit or terminating it a little bit differently can drastically change the common mode current. So we don't control that, but we have complete control over the common mode voltage that drove that cable relative to the chassis, or our product has complete control over that. And if your common mode voltage driving that common mode current is less than a millivolt, actually theoretically less than 0.2 millivolts, but less than a millivolt as a practical matter, there's not enough voltage to put enough current on any cable, no matter how they arrange it, to cause a radiated emissions failure. So your goal as a designer is don't drive that cable relative to the chassis. Don't drive this big antenna part relative to this other big antenna part with a common mode voltage greater than a millivolt. And that's relatively straightforward to do. If you know what to look for, there's a limited number of ways you can drive a cable relative to the chassis.
What I'm hearing here is search for the source of the common mode voltage and insulate or reduce the amount of voltage getting to your affected conductors, rather than trying, let's say, common mode filters, common mode chokes, unless you really need them or you can prove that you need them.
Oh, that's right. We never design in a common mode chokes for balanced power inputs or unbalanced signal ports make perfect sense. We see common mode chokes on unbalanced power inputs, which actually makes no sense. But common mode chokes is a different thing. Ferrites, on the other hand, just clamping a ferrite around a cable, a great tool if you're troubleshooting and just need something that's going to give you a few dB quick. We would never design that in, but if you've made a mistake in the design and you're driving too much common mode current onto the cable, that can get you through a test. I don't know that it's a good... The fact that you had the problem means there's a problem with the design, and that ferrite may not work. It may have worked in that test environment, but it may not be working as well in the real world. So I'm not a big fan of the ferrite clamps, but that's because I don't do troubleshooting.
Right.
I do design. I guarantee the design will be compliant. So we don't do troubleshooting. But if I were the person doing the troubleshooting, I'd want to have a good supply of ferrite clamps.
Sure. Makes sense. And then one last thing about common mode chokes. I think if people start searching for common mode chokes, they will start to notice that there are certain, highly integrated, right, ICs that are, common mode filter circuits, or I guess you could call them common mode chokes if you want to, that are standardized for specific interfaces, right? So a common one is like USB or HDMI or DisplayPort. And I mean, they list it right there in the component description on the distributor website and in the data sheet, right? So clearly the manufacturer is marketing to those interfaces. And I think the implicit suggestion is that, well, if you're using this interface, you should use this component. Do you buy that or not?
I do. I think common mode chokes on balanced signal interfaces can't hurt. I mean, and often are necessary. Actually, I've seen that on CAN. Often where you need that common mode choke because the CAN driver was actually creating a common mode. It wasn't a very good, but also HDMI, LVDS, USB, all of these high-speed interfaces that use these pseudo-differential drivers, they actually don't get that pseudo-differential switching perfect. So every time they switch, there's a blip of common mode. And the differential is not going to be a problem for you unless you change your balance somewhere. But that common mode blip, you need to do something about that, perhaps. Or you often need to do something about that. It's too much. And a common mode choke, that's a good tool or a good device to have in the way before you go out on the cable. So yeah, I don't see anything wrong with that. It's the common mode chokes that are on DC power supplies where you're going into a buck or a boost converter, clearly unbalanced. One side's got a really good connection to the ground plane. The other side's routed on a trace. You should not have a common mode choke on that because common mode chokes make things balanced. You are unbalanced. That conversion from unbalanced to balanced is it's converting some of your differential to common mode.
I see. Okay. We've talked about a lot here, and I think we're running up on time. But before we wrap up, I just wanted to give you a quick opportunity. If you could just tell folks how they can get in contact with you and some of the stuff that you're doing through LearnEMC.
Oh, yeah. Well, our website, learnemc.com, we're trying to get as much free information up there, tools, calculators, course notes, things like that up there as we can. And to contact me, I guess use the contact information on our website would be the best way to contact me. Well, or if you want to get me directly and you've watched this podcast, my email address is just my last name, Hubing at learnemc.com, and you can email me directly. But yeah, we're trying to, I consider myself retired. I retired 10 years ago, and I'm just doing what I'm doing now because I love doing it. And so, yeah, I don't like to view this as I'm trying to sell anything. That we do, like our courses, our live courses, we charge for that because we have to limit the number of people attending to a reasonable number. And but most of the stuff we do, and we're trying to get more of it just out there for free. So.
Okay. Well, I hope anyone that's interested will go check out your website. We'll have a link in the video description, and I'm sure some folks will want to follow you on LinkedIn. So again, also check out the link in the description, and you'll be able to learn much more about EMC from an expert.
Yeah, actually, I will put in, if I can, I will put in a plug for one thing. So I write an EMC question of the week on the website.
Yes, I have seen that. Yes.
And usually what happens is I'm on LinkedIn and I'll see something outrageous that somebody says. And I don't like to be a curmudgeon on LinkedIn, and sometimes I am, but I don't like to be. But what I'll do is I'll make the question of the week where I put the exact same thing I saw on LinkedIn with what I consider to be the correct interpretation or the correct answer. Anyway, it's a question, and then the answer usually has enough explanation to kind of explain why it's meant to be educational, not really a quiz or anything. But so I'll put it, that's completely free, and I'll put in a plug for that.
Awesome. Okay. Well, I hope everyone checks out the links in the description. They can learn more. Todd, thank you so much for being here. As I said when we started, it's been too long since I've considered having you on, and I'm glad we were finally able to do this.
Yeah, it's been fun. Thanks for inviting me.
Absolutely. To everyone that's out there listening, we've been talking with Todd Hubing, president of LearnEMC. If you're watching on YouTube, make sure to hit the like button, hit the subscribe button. You'll be able to keep up with all of our podcast episodes and tutorials as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time. Thanks, everybody.